Hello everyone, and welcome to this first recording in the Class 11 series of lecture note recordings. Today we'll be looking at dissecting how multiple bonds are treated for first point of difference considerations in the assignment of stereocenters, and we'll also be introduced to things called Fisher projections. So, first, functional groups and the first point of difference considerations for the assignment of R and S. So, let's pretend that we have a carbon that has a double bond to another carbon that is attached to a stereocenter. That's what this squiggly line means. It means we've broken that bond between this group and some stereocenter. How do we treat this carbon? Well, we would simply treat it as a carbon that's bonded to two other carbons, and of course R double prime, whatever R double prime is, and of course the other carbon that it's bonded to is still bonded to R and R prime. So let's use that and see if we can assign a stereocenter for this particular dienyl alcohol. So, of course, our oxygen is our first priority, our hydrogen is our fourth priority, it's already in the back. So then we have to decide, is this is this carbon a higher priority than this carbon? Well, if we diagrammed this arm, which we've already assigned for a second priority, what would we see? Well, we'd see a carbon that's going to our stereocenter, that's this carbon here, going to our stereocenter. But we've cut that off, and so how do we treat this carbon? Well, we treat it as a carbon that's bonded to a methyl group, and then it has two bonds to two other carbons by virtue of that double bond. How about this arm? How do we treat this carbon in particular that we've already labeled our third priority arm? Well, we treat it as a carbon that has two bonds to carbon, but this carbon is also bonded to a hydrogen. It's not explicitly drawn in this bond line diagram, but I know that you know that carbon can have four bonds, and so if one bond is taken up going to the stereocenter, which is cut by this squiggly line, and then it has a double bond to another carbon, that leaves one other bond for it, and for a bond line we assume that that's a hydrogen atom. So obviously two carbons and a hydrogen is lower priority than 1, 2, 3 carbons. So that's why this arm got second priority and this arm got third priority. And then if we connect 1 to 2 to 3, we're going in a clockwise motion. So this is an R stereocenter. Triple bonds are treated similarly. So say you have an alkynyl carbon that's bonded to some stereocenter. How do you treat that triple bond? Well, you simply treat it as a carbon that's bonded to three other carbons. And yes, the other carbon is bonded to whatever R is. So for example, what about this molecule? Here we have already assigned our priorities. We've got hydrogen in the back, which is fourth priority. We know that. This carbon is first priority. Why is this carbon first priority and this carbon second priority? Well, this carbon is bonded to three other carbons. This carbon is bonded to three other carbons. So we have to go one carbon out. And so any of these carbons, if we move outward, are bonded to three hydrogens. Well, if we move out one carbon along our alkynyl arm, that carbon is treated as what? A carbon that's bonded to two carbons, and in this case, R is hydrogen. So that's a higher priority than any of those methyl groups. So that's why our alkyne gets first priority, this arm gets second priority, and of course this arm gets third priority, and if we connect 1 to 2 to 3, we're going clockwise. So this is an R stereocenter. How about a carbon with a double bond to oxygen? Well, if you have a group attached to a stereocenter, which is a carbon that's double bonded to an oxygen bonded to some R group, we treat that as a carbon bonded to 2 oxygens, and whatever R is. So, in summary, we've written up a summary. Double and triple bonds are treated as if they are single, and the atoms in them are duplicated or triplicated at each end by the respective atoms at the other end of the multiple bond. And of course, you've got to practice, right, to become adept at assigning stereocenters for molecules. So one more example, and then we'll launch into Fisher projections. So here we have chlorine. Chlorine's our highest priority. Hydrogen's our lowest priority. It's already in the back. This carbon is treated as a carbon bonded to 2 other carbons and a hydrogen, whereas this carbon is treated as a carbon bonded to 1 other carbon and 2 hydrogens. So that's why this arm gets second priority and this carbon gets third priority. And so attaching, so connecting 1 to 2 to 3, we're going clockwise, so that's an R stereocenter. So finally, Fisher projections. These are the molecules that want to come up to you and give you a great big hug. So how do we treat them? Horizontal groups or substituents are projected up and out of the plane of the page. That's like their arms, coming out to hug you. And vertical substituents are projected back. So I've symbolized that by giving wedges to our horizontal groups, our hydroxyl group and our hydrogen group, and then giving dash bonds to our other groups. Now, Fisher projections have their own rules. They're not exactly bond line structures. So we'll see what those rules are, right? Of course, like I said, we draw straight lines. We typically don't, detail the carbon atoms with a big C, similar to bond line, but we have to remember that these horizontal substituents are coming up out of the plane of the page and the vertical substituents are going back. This Fisher projection is the same as this one. We simply rotate around a carbon-carbon single bond, so we rotated that hydroxyl group off to the other side, which is fine, we can do that. Again, we rotated this around this carbon-carbon single bond to switch the positions of the oxygen and the hydrogen. These are all the same molecule. So don't let free rotation fool you. You can rotate around sigma bonds in Fisher projections. So Fisher projections are different than bond line diagrams. If you rotate a Fisher projection by 90 degrees, simply according to the rules that the horizontal substituents come up and the vertical substituents go back behind the plane of the page, then you change the stereocenter. So for example, this molecule is an R stereocenter. You can almost see it. The hydrogen comes up and the oxygen comes up. If you could twist the molecule away from you, so rotating it a little bit on the right side, you can connect 1 to 2 to 3, which you've assigned in terms of priority, and you can see that that's an R stereocenter configuration. You could build yourself a model to prove it to yourself, or you could probably ask me to do an interpretive dance at the next class session. Interpretive dances are always fun, especially when you can integrate them into organic chemistry. If we rotate this Fisher projection by 90 degrees, you can see here, our priorities, our assignments are still the same. However, this stereocenter is now an S stereocenter, which, that doesn't happen with bond line diagrams. So that's why I wanted to emphasize that Fisher projections are different than bond line diagrams. Similarly, if you interchange 2 substituents, you change the stereocenter. So what did we do here? We interchanged the hydroxyl group and the hydrogen group, and we left the other 2 groups the same. And again, we got an S stereocenter. We went from R to S. And of course, according to that rule, if you interchange all four groups, that's like interchanging two groups and then interchanging two other groups, the stereocenter stays the same. So for this Fisher projection, we are R because we just interchanged these two groups to reach this Fisher projection that looks like we interchanged all four groups from what? From this Fisher projection up here. So that pretty much ends our introduction to Fisher projections. We'll continue in the next video looking at bond line structures. All right.